So far in our study of mathematics, we've dealt primarily with real numbers. Today, we're going to expand our horizon a bit and learn about a new type of number, which we call a complex number. Now, before we can properly address complex numbers, we need to take a look at a couple of other things. So let's start with the square root property, which simply states that if x squared equals k, then x must be either positive or negative square root of k. Now, this makes sense if you think about it. For example, if, let's say, x squared equals 4, right? The numbers that you can square to get 4, we know are 2 and negative 2, which happen to be positive or negative square root of 4, right? So x equals plus or minus square root of 4, or x equals plus or minus 2. Now, this doesn't just work with nice perfect squares, of course. If x squared equals 11, for instance, we get the same result. X equals plus or minus square root of 11. Now, if you take the positive square root of 11 and square it, what do you get? You get 11. And if you take the negative square root of 11 and square it, you also get 11. So this formula makes sense. It can easily be proven using a little bit of algebra. But the whole notion of complex numbers came about when we tried to look at a question like solve x squared equals negative 1. Now, this square root property is universally applicable. So that means I can go ahead and apply it to this scenario as well. And I get x equals, here my k is negative 1, so I'm just going to get x equals plus or minus square root of negative 1. So we ask ourselves, well, what is the square root of negative 1? When I look at the square root of 4, for instance, I know that I'm looking for a number that when I square, I get 4. That number, of course, is easy, right? In this case, this is the positive square root of 4, so that's just going to be positive 2. And if I look at the negative square root of 4, that's going to be negative 2. So these are the two numbers that I can square to get 4. This is called the principal square root. The positive square root of a number is called the principal square root of it, and this is called the negative square root of 4. Now, but what number can I square to get negative 1? Well, if you think about it, it can't be a real number, because what happens when you take any real number and square it? Whether it's positive or negative, when you square it, in both cases, you're going to end up with a what? With a non-negative result, right? The worst case scenario is 0, right? So what to do? Well, we go ahead and accept it for what it is. Now, because we're going to be dealing with this quite a bit, we're going to give it a name. Since it's not real, of course, we chose the name imaginary number. So this square root of negative 1 is called the imaginary number I. Now, I have to warn you that sometimes in classes like electrical engineering, because they use I for current, they use the letter J for the square root of negative 1. But in purely mathematical classes, we use I, okay, for the complex number square root of negative 1. Now, you may say, well, why should I even care about this number or study this number if it's not real, right? What good does it do? Well, the fact that it's not real just simply means it doesn't live on the number line. It doesn't mean that it's not extremely useful. In fact, one of the most famous people you may know about, Einstein, much of what he did with respect to, say, the fourth dimension, etc., has to do with using of this particular number right here, which is the square root of negative 1. If you think about it, since Einstein considered the time to be the fourth dimension, and we have the other three spatial dimensions which are perpendicular to each other, the three axes x, y, and z, the way to bring in another dimension which is also at the same time perpendicular to all of them was using this number I. So never be mistaken about the fact that this number is not important. It's extremely important, okay? That's why we study it. So what we want to do now is take a look at a few powers of I, just to get comfortable with the notion of I, because it's an interesting way that the powers of I work out. The first power of I is just, of course, I itself, which is the square root of -1. Now, the second power is going to be square root of -1 squared. Now, the fact that the square root of any number squared is the number itself is also a universal fact. We'll look at that a little more closely in the next slide, but for the time being, just remember that that's just going to be -1. So I squared is -1. Now, how do we get I cubed? Well, once we have I squared and I, it's easy to get I cubed, because you can think of that as I squared times I. Now, I know that I squared is -1 times I, which I can just write as I, because I could write it as square root of -1, but I know what that is. That's just I, right? So it's -1 times I, so it ends up being -I. Notice I have that here in this table. I is the square root of -1. I squared is -1. I cubed is -I. How about I to the 4? Well, that's easy. That's just going to be I squared, right? So that's -1 squared, quantity -1 squared, which is just 1, right? So the fourth power of I actually becomes 1. Now, what is the fifth power of I? Well, think about it. I can think of that as I to the 4 times I, right? I know what I to the 4 is. That's 1. So that's 1 times I, which is just what? Back to I. That's why I have this graphic for you. You start with I, you go to I squared, you go to I cubed, and then I to the 4, and then once you go to the next power, that's back to I. We call this a cyclic group of order 4, okay? Because the group consisting of the powers of I only has 4 unique members. Like I to the 6 will be I to the 4 times I squared. That's 1 times -1, so it's just what? -1, back to I squared, see? The next one, I to the 7, that's I to the 4 times I cubed, which is 1 times -I, which is what? -I, on and on and on, right? Now, the easiest way to actually figure this out is not using the fourth power necessarily, but using the second power, because that's a nice power. It's -1, and it's easy to work with. So I to the 8, I'm going to look at as I squared to the power of 4. I know what I squared is. That's -1. When I raise it to the power of 4, I'm just going to get 1, okay? And -1 raised to an even power is always just 1. Now, see if you can figure out these next few before you continue. See if you can come up with a way to come up with those before you watch me do it. All right, so let's assume that you've done that. So I can think of this I to the 42. As long as the number is even, it's a very easy process, because I'm just going to write it as I squared to the power of what? Well, remember the power rule. This exponent times that exponent out there will have to be 42. So if I just divide 42 by 2, I get 21, right? Now I know I squared is -1. Now I get -1 to the power of 21, right? What's -1 to an odd power? -1, okay? I to the 100, again, I can think of it as I squared to the power of what? Did I hear you say 50? I agree, okay? Remember, the power rule is x to the m raised to the n is x to the mn, right? So we're applying that rule, but in reverse, right? So that's going to be -1 to the power of 50. So a -1 raised to an even power, that's always 1. How about I to the power of 203? Well, it's not even, but I can get to the best nearest thing, which is I to the 202, right? That just leaves me an I, right? So it's I to the 202 times I, which is I squared to the power of what? 101, right? Times I. Now I squared is negative 1 to the power of 101. That's going to be negative 1 because it's an odd power. So it's negative 1 times I. So it's going to be negative I. How about I to the 1001? If you haven't done it already, please try it on your own, okay? All right. So that's I to the 1000 times I, right? Which is I squared to the power of 500 times I. Now that's negative 1 to the 500 times I. Now I know negative 1 to the 500, that's negative 1 to an even power, so that's just 1 times I, which is going to be I. Okay? So notice that no matter what power you look at, it's going to be one of these 4 powers, right? That's why we call it a cyclic group of order 4. You only get one of these 4 results, I, negative 1, negative I, or 1. Okay, so make sure you're comfortable with these before we proceed. Okay, now that we know what I is, we can formally define the set of complex numbers. The set of complex numbers which we use the script letter C for is basically the set that is defined first of all using set builder notation, because there's no way for us to list all the elements in a simple way like we do with the set of natural numbers or integers or anything like that. So we define it using set builder notation. So we describe what's in it rather than list what's in it, right? Such as in the roster method or the listing method. So we say the set of complex numbers is the set of all numbers of the form a plus bi, such that, this bar here means such that a and b are members of the set of real numbers, and I is what we just defined to be square root of negative 1. So when you have a complex number, notice that we usually use the letter X for unknowns in the set of real numbers. We use the letter Z as the counterpart for complex numbers. So let Z equal A plus BI. Then we say that A is called the real part of Z and B is called the imaginary part of Z. Notice just the B without the I, right? So A is the real part of Z, we write it like this, RE of Z. B is the imaginary part of Z, which we write as IM of Z. Now, let's say we look at a few complex numbers and determine the real part and the imaginary part and then graph it, okay? So here, of course, this is given in our standard A plus BI form. That's called the standard form of a complex number. And so clearly the real part of Z is 4 and the imaginary part of Z is 3. The graph of 4 plus 3i is easy. Once we deal with the set of complex number, we take our familiar Cartesian coordinate plane and use it in a different way. So this no longer is called the Cartesian coordinate plane because I'm thinking of this axis as not just y, but yi. In this format, this is called the complex plane. So when you see the I on the y-axis, don't think of it as the Cartesian coordinate plane anymore. Think of it as the complex plane, which I have written right there anyway. Now, to graph 4 plus 3i, very simple. Think of it as if you're going to graph the point 4, 3, okay? It's not what you're graphing. You're graphing a single point, this single complex number, but the procedure is the same as graphing the ordered pair 4, 3. So you just go 1, 2, 3, 4 in the x direction, and you go 1, 2, 3 up in the yi direction. Now this point here is not the ordered pair 4, 3. Keep that in mind. This is just a reference, you know, for how to graph it. It's the single complex number 4 plus 3i, just like that. So you write it like that, and it's not an ordered pair, it's a single point in the complex plane. How about this one? Z equals -6 minus I. Notice that the real part of Z is -6. The imaginary part of Z is -1. So we're going to graph it as if we were going to graph the ordered pair -6, -1, right? So we go 6 to the left of the origin, 1, 2, 3, 5, 6, and we go down 1 in the y-I direction. There we plot the point and we call it the single complex number -6 minus I in the complex plane, okay? How about this one? Well, you're saying there is no A. There is an A. It just happens to be what? 0. So you can think of this as 0 minus 5I. So the real part of this complex number is 0, and the imaginary part is -5. So you start, so that the reference point for our Cartesian coordinate plane would be 0, -5. So you graph it as if you were going to graph 0, the ordered pair 0, -5 in the Cartesian coordinate plane. So you would go start at the origin, just go down 5 units, right? So mark it and just call it -5I. You can also write 0 minus 5I. It's the same thing. How about this one? You're thinking, wow, there's nothing complex about that. That's a real number. Well, yes, but this is the interesting thing. You can take any real number and write it as the real number plus 0I. So, which tells you the set of real numbers, which happens to be right there, is just a subset of the set of complex numbers. And in fact, it's a proper subset. So the real part of Z here is 3, and the imaginary part is 0. So we just have to start at the origin and we go to the right 1, 2, 3 units. So there is the graph of 3, as you would expect, right? Now here's the interesting thing. A complex number whose real part is 0 is going to fall exactly on the y-I axis, and that's why we call it a pure imaginary number. So a number like -5I is called pure imaginary. We'll look at that definition again soon. Now, a complex number whose imaginary part is 0 just becomes a what? Just becomes a good old real number. So, and that's exactly what we call it. It's a real number, like that. So, what we used to consider to be the whole universe of numbers, the real number line, is now just one part of the much larger what? Complex plane. All right, so the real number line is no longer the big honcho on the block, right? Now we have a set which is much more expansive than the set of real numbers. All right, so we already talked about this, but we'll formalize it here. We want to talk about the types of complex numbers. A complex number Z, written in this form Z equals A plus BI, is said to be in standard form. Recall that in standard form, the A becomes the real part of Z, and B, without the I, is just called the imaginary part of Z. A complex number in standard form, Z equals A plus BI, for which B is 0, that means what? The imaginary part is 0, just becomes a what? A real number. So a complex number in standard form, whose imaginary part is 0, is a real number. A complex number in standard form, Z equals A plus BI, for which the real part is 0, A, is called a what? Pure imaginary number, okay? Because it has no real part. It only has an imaginary part. The real part is 0. Now, any complex number Z equals A plus BI for which the imaginary part B is not 0, that is B not equal to 0. Now, this is true whether A is 0 or not, is called the non-real complex number, because it has an imaginary part that is not 0. As long as B is not 0, you're dealing with a non-real complex number, okay? So now we want to kind of summarize everything we know about these sets of numbers we've been studying all our lives, right? Every real number, as we know, can be written as a plus bi with b equals 0. Therefore, the set of real numbers itself is a proper subset of the set of complex numbers. We've already seen that. I've already shown it on the graph. So we say the set of real numbers is a proper subset of the set of complex numbers. Now, in fact, we know a lot more than that. We know that the set of natural numbers is probably the first set we ever study, because those are the counting numbers, 1, 2, 3, 4, etc. Itself is a subset of the set of whole numbers, which is nothing but the set of natural numbers with 0 thrown in as well, right? So 0, 1, 2, 3, 4, etc. And which is itself a subset of the set of integers, which you know includes all the whole numbers and their opposites. Now, they are themselves a subset of the set of rational numbers, which are all the fractions whose numerator and denominators are integers and whose denominator is not 0. And then we know that there is this other really large group of numbers that are subsets of the set of real numbers, which are not rational, like the square root of 2, pi, right? When you write these numbers as a decimal number, the decimal representation neither repeats nor terminates. With a rational number, if you write it in decimal form, it's either going to repeat or terminate, no other option. But with these guys, the set of irrational numbers, which we refer to as p as opposed to q, is the set whose decimal form neither repeats nor terminates. Notice that the entire set of real numbers represented here is a subset of C, and then we have this other group that has nothing to do with these, because these have an imaginary part that's not 0. So we have the reals and we have the non-complex, non-real complex numbers. Now, if you know about the complements of sets, here the universal set we're looking at is C, and if this is R, this is just the complement of R, okay? So, and we can describe them as such: all numbers of the form a plus bi, where a and b are real numbers and b is not 0. That's only for this part that we are looking at, the non-real complex numbers. So now this gives us a complete picture of all the sets of numbers that we've studied so far. All right, now that we know what complex numbers are, let's go ahead and learn how to operate on them. Okay, so we're going to look at operations on complex numbers. Before we go further, we need to talk about the generalized product and quotient rules for radicals. Many of you are under the impression that if you take the square root of x times square root of y, you get the square root of x times y. Now, because you've been dealing with these with the radicands here, remember the number under the radical is called the radicand, being non-negative, this is completely true, okay? And so is this, that if you take the square root of x divided by the square root of y, you get the square root of x over y. Yes, these are definitely true for whole numbers. In fact, I don't just mean whole numbers, I mean for non-negative numbers, right? Real numbers. But as it turns out, they're only going to be true if these two numbers are not both negative, okay? Now, if they are both negative, then we're going to have to deal with them a different way, and we'll get to how to do that in a minute. This rule, however, the fact that the square root of any number squared is itself, is universally true for all x, okay? So this rule from the past persists. In fact, we had to modify these two rules out of respect for this rule so that this rule becomes true, okay? Because let's see what would happen if we let these stay in power, in force, right? Then the square root of -1 times the square root of -1 would have become the square root of -1 times -1, which would be the square root of 1, which is 1. And of course, as we know, this is not true. The square root of -1 times the square root of -1 is the square root of -1 squared, which is -1. So to preserve this fact, we had to modify these two rules and limit them to being true only if the two radicands are not both negative. Okay, very important to keep that in mind. We'll see what you need to do if the radicands are negative. All right, here we're going to take a look at these problems, and we're going to simplify them. And when we say simplify, we're going to leave no perfect squares under any radical. We're not going to leave any negatives under any radical, and we're not going to leave any radicals in any denominator. Now, in this case, we're not going to run into that, but these are the three general rules of simplifying radical expressions of this type, which I'm stating for you. So let's go ahead and see how we would do that. Well, the best way to approach this, let's only deal with the 28 for a minute. We're going to find the prime factorization of 28 using a very simple procedure. We're going to ask ourselves a question: what is the smallest prime number that goes into 28? Now, 28 is an even number, so that's a trivial answer. It's 2, right? Remember, the smallest prime number is 2 anyway, right? 1 is neither prime nor composite. So we go ahead and write the 2 to the left of 28, and we go ahead and divide. 28 divided by 2 is 14. Write the result on this side, below the 28. Repeat the process. What's the smallest prime number that goes into 14? 14 is still even, so the answer is going to be 2 again. And when we divide, we get 7. We write that under the 14. Now, what's the smallest prime number that's going to go into 7? Remember, 7 is a prime number itself. So the only prime number that's going to go into it is itself. So we write 7, and then we divide, we get 1. Once you hit this 1 down here, the process of prime factorization is complete, and you have your prime factorization of 28 right here on the left side. So I can rewrite the square root of -28 in this way. That's the square root of -2 squared times 7, right? Now I'm going to use the fact that the square root of x times the square root of y equals the square root of xy if x and y are not both negative, and break this up in this way. I'm going to break it up into 3 parts. In the first part, I'm going to put the perfect square part, so the 2 squared. In the second part, I'm going to put the non-perfect square part, the 7, and the negative I'm going to handle in this last radical. I'm just going to put a -1. So notice, if you multiply -1 by 2 squared by 7, you get exactly this, right? And we were able to do this because, for example, square root of -2 squared, these are not both negative, so we can do that. We can apply the rule, right? So now the square root of 2 squared is just, of course, 2, right? So we have 2 radical 7, and finally we write the square root of -1 in its other form, which is what? I. So that would be the simplified version of this problem. Make sure you understand that, and with these, I would like you to try them yourself and then come back. All right, so welcome back. So we're going to go ahead and take 500 and find the prime factorization, right? So what goes into 500? That's prime and the smallest prime. So it would be 2. We divide, we get 250, write it on the right side. Again, we repeat the process. 2 works, 125. I can't use 2 anymore because this is not an even number. I try to see if I can use 3. Remember, you add the digits. If the sum is divisible by 3, then the number is divisible by 3. 1 plus 2 is 3 plus 5 is 8. That is not divisible by 3. So I go ahead and move to 5. So when I divide 125 by 5, I get 25. And once again, I can go with 5. 25 divided by 5 is 5 again. And finally, 5 is a prime, so the only number that'll go into it is itself, which is prime. And you get 1. Remember, once you reach 1 on the right side, the process is complete. You have the prime factorization right here, very nicely laid out. So you can write 500 as 2 times 2 times 5 times 5 times 5. So I'm going to break up, so I'm going to rewrite square root of negative 500 as negative 2 squared times, I'm going to do a trick, and instead of writing 5 cubed, I'm going to write 5 squared times 5. You'll see in a minute why we do that. Because now when we go to the next step and we want to break it up into 3 radicals, it'll be much easier. Remember, the negative 1 will go in the last one. In the first radical, we're going to put the perfect squares, so 2 squared times 5 squared. And in the middle one, we're going to put the non-perfect square, so just the 5 by itself. So now, the square root of 2 squared times 5 squared, that's just 2 times 5. And then radical 5, and then the square root of negative 1 is just I, right? So we end up with 10 radical 5 I. Now this is just a multiplication, so sometimes you'll see books or other people refer to this as 10I radical 5. Now most mathematicians, however, prefer this form because it can easily be put into the standard form of a plus bi, okay? So we usually like to put the I in the end. All right, how about the square root of negative 16? Square root of negative 16, notice that's, 16 is a perfect square, so we can do this really quickly. We can just say that's the square root of 16 times the square root of negative 1, and of course the square root of 16 is 4, so we just get what? We get 4i, just like that. All right, so that's how we take care of these simplification problems. All right, so this is where you're going to have to be careful. Here, both of these numbers under the radicals are negative, so you can't just multiply under the radical, right? And say, oh, this is the square root of 14. Can't do that. Remember, that rule only applies if these two radicands are not both negative. So what if they are? Simple. Go ahead and just write the first one as the square root of 7 times the square root of negative 1. Write the second one as the square root of 2 times the square root of negative 1. Now, for these two, you can multiply under the radical because they're both positive, right? So we get square root of 14, and the square root of negative 1 times square root of negative 1 is just the square root of negative 1 squared, which is just what? Negative 1. So we end up with, remember, this whole thing is negative 1. So we get negative square root of 14, like that. Okay? So I could have also said square root of 7 times I times square root of 2 times I, which is the square root of 14 I squared. And if you recall, I squared is what? Negative 1. So again, you'll get the same thing. Okay? So whether you work with square root of negative 1 or I, makes no difference. Okay, go ahead and try these next two and see what you get before you join me back. All right? So here, these are both perfect squares under the radical, so we don't need to go through the prime factorization business and all that. So I'll just go ahead and do the same thing. That's square root of 4 times square root of negative 1 times square root of 100 times square root of negative 1. This time I want to do it in the form of I, so that's 2i times 10i. So I can multiply the 2 and the 10. That's 20 I squared. Now I know what I squared is. That's negative 1. So I get 20 times negative 1, which is what? Negative 20. Now how about this one? Well, this is like almost a trivial problem. Remember, the square root of any number squared, or I should say quantity square root of any number squared, is itself, right? So here, we're just going to get, that's just the square root of negative 26 squared, which is just what? Negative 26. Now, could you have taken the longer route? Of course, you could have said square root of 26 times the square root of -1 times the square root of 26 times the square root of -1. Now, square root of 26 times square root of 26, that's just 26. That's I and that's I, so you get I squared. Again, I squared is -1, so you get 26 times -1, which is -26, okay? Same result, of course. All right, so that's how we approach those. Okay, so here we're going to deal with these fractions. So we get square root of 300 times the square root of -1 on the top, and square root of 100 times square root of -1 on the bottom. Now, these two, they're both non-negative. The radicands are both non-negative, so we can go ahead and apply this rule. Square root of x over square root of y is the square root of x over y. So we get square root of 300 over 100. Now, when it comes to division, it kind of is interesting because notice these do in fact cancel out. You can always cancel anything with itself, right? So these will cancel out just like regular numbers do, right? Real numbers. And you're just going to end up with what? Square root of 3. Okay? All right, how about this one? Well, square root of 320 times square root of -1 over square root of 64 times square root of -1. Again, the square root of -1's cancel. Now down below, I just have an 8, right? So I just need to figure out the prime factorization of 320. So I know I can start with 2, that gives me 160, 2 gives me 80, 2 gives me 40, 2 gives me 20, 2 gives me 10, 2 gives me 5, and 5 gives me 1. So I have 2 to the power of 1, 2, 3, 4, 5, 6. So that's the square root of 2 to the 6 times the square root of what's left? 5, right? 2, 4, 6, yeah. Now, what is the square root of 2 to the 6? In other words, what power of 2 do you have to square to get 2 to the 6? Think about it. It would have to be what? 2 cubed, right? So the square root of 2 to the 6, that's 2 cubed, times square root of 5 over 8. But 2 cubed is also 8. So that's 8 radical 5 over 8. The 8's cancel out. What do we end up with? Just radical 5. This first one ended up being radical 3. All right. Finally, this last one. To solve this one, we're first going to use the multiplication version of this rule up here, which is square root of x times square root of y equals square root of xy. And of course, we know that's true as long as they're not both negative. We mean they're radicands. And so here we can go ahead and write the square root of -80 as the square root of 80 times the square root of -1. And since one of the radicands is positive, we can apply that rule over square root of 5. And now we're going to apply this rule up here, the quotient rule, for radicals. Given that both of these radicands are positive, we can safely use that rule. So we can put them under one radical. So we get square root of 80 over 5 times square root of -1. Now 80 over 5 is 16, so we get square root of 16 times the square root of -1, which of course we recognize as none other than I. So our final answer will be 4i. And that's how we handle that one. Now, combining, which basically means adding or subtracting complex numbers, is super simple. Basically, First, we're going to go through, see if we can drop the parentheses if they're not needed. Once we've dropped the parentheses, we're just going to combine the real parts and then combine the imaginary parts. That's it. So I notice here, these parentheses are not really doing anything. They're just placeholders, and so are these. So we can drop all those parentheses. So we end up with 5 plus 2i, and positive times negative 8, that's just minus 8, and then plus 10i. So now I'm going to combine these two real parts of these two complex numbers, and I'll combine these two, right? The parts which have an I attached. So 5 minus 8, that's negative 3, and 2i plus 10i will give me 12i. So there it is, as simple as that, okay? So negative 3 plus 12i. So go ahead and make sure you try these next ones first before you continue. All right, so we're going to get rid of the parentheses first. The first set of parentheses is just a placeholder. We can drop it. Not so quickly with this one. There's a minus here, so an invisible negative 1 that needs to be distributed. So we end up with plus 11 plus 3i. Now, just like before, combine the negative 15 and the 11. Also combine the 7i and the 3i. So we end up with negative 4 plus 10i. Just like that. Okay? Here, same thing, it just we happen to have what? Fractions, no big deal. So we have 3/4 plus 1/2 i. The first pair of parentheses can be dropped. We're going to distribute the negative into the second pair. So we get negative 5/6 minus 1/3 I. Now I will put the 3/4 and negative 5/6 next to each other because I'm going to be combining fractions. And I'll put the plus 1/2 I minus 1/3 I next to each other as well, okay? So with these two, the LCD is least common multiple of 4 and 6, 12 should do. So I'm going to make both of those 12. That means I need to multiply this 4 by 3, which means I will of course do the same thing on the top as well. For the 6, I need to multiply it by 2 to get 12. So I'll do the same to the top, to 5. And the new numerators are now 9 and 10, okay? And we have a subtraction there. And then plus, now with these two, the LCD is 6. So I'm going to make both of those denominators become 6. 2 has to be multiplied by 3 to get 6, right? So we do the same to the top. We always do the same thing to both numerator and denominator. This 3 has to be doubled to get 6. So we double the top. So the new numerators now are 3 and 2, right? And don't forget, both of these are multiplied by I, right? So combining these two will give me negative 1/12. Combining these two will give me 3 minus 2, which is 1. So 1 plus 1/6 I. And notice that that answer is in standard complex form. That's it. It's as simple as it is when it comes to combining complex numbers. All right, when it comes to multiplying complex numbers, we do them exactly the same way that we multiplied polynomials. We use the same techniques. So let's go ahead and try it. So like here, imagine this were x, right? X and x. What would happen? You would get x squared, right? Same thing here. So we multiply the 7 and 10. That gives us 70. And the I times I is just I squared. You just have to keep in mind that I squared is negative 1. So this becomes 70 times negative 1, or just what? Negative 70. Try these next ones on your own before you continue, please. Okay, -7 times -9, that's 63, positive 63, and then we have I squared, right? Again, I squared is -1, right? So we get 63 times -1, which is -63. Here we're going to distribute the 3i, right? So 3i times -8, that's -24i. And 3i times positive 7i, that's going to be positive 21i squared, right? Don't forget, I times I is not just I, it's I squared, right? Which we know is what? -1. So we have -24i plus 21 times -1. So that's -24i minus 21. And of course, standard form of the answer is going to be a plus bi, so we'll write the -21 first and then the minus 24i. Now we've given the answer in standard complex form. For these, you just distribute just like you would with polynomials, right? So first, we'll go ahead and distribute the 2. When finished, we'll distribute the 8i. So 2 times 4 is just 8. 2 times -7i, that'll be -14i. Positive 8i, we're distributing the 8i now. Positive 8i times 4, that's positive 32i. And positive 8i times -7i, that's going to be -56i squared. Again, I squared is -1. So we're going to have 8 minus 14i plus 32i. -56 times -1 becomes plus 56. Now we'll combine the 8 and the 56. That will give us 64. And we'll combine these two. 32 minus 14, that's 18. Positive 18, so plus 18i. Just like that. Very simple, okay? Here, of course, we remember that a plus b squared is not a squared plus b squared. Remember that. These you have to write it out and distribute. So 8 plus 9i times 8 plus 9i. So we end up with, distribute the 8, so you get 64 plus 72i. Plus, now we're going to distribute the 9i, so plus another 72i, plus 9i times 9i, that's going to be 81i squared. We replace the I squared with a -1, so we have 64 plus 72i plus 72i plus minus 81, right? Positive 81 times -1 is -81. Now, 64 minus 81, I'm going to go ahead and be safe. You can always do it by hand, that's fine. So that's -17. And that's just going to be 2 72s, which is 144, plus 144i, okay? Now, I want to show you a couple of other ways you could have handled that. So let me copy it into a whiteboard and show you a couple of other things you could have done. All right, I'll be back in a minute. Okay, so I wanted to show you a couple of other ways to handle this problem. One is, if you recall, we have this formula for the square of a sum, which we studied in algebra, which worked like this. So if we have quantity f plus L squared, now we can work that out, of course, by just writing it twice and foiling, or we could use a table, which I really like using this method. So what we do is we just write f plus L and f plus L. We write one of the factors horizontally, the other vertically, then we multiply like a times table. So f times f is f squared, f times L becomes plus fl. Here, positive L times f, again we get plus fl, and plus L times L gives us L squared. So we notice that here inside we can combine these two, so we get f squared plus 2fl plus L squared. So f first, last, right? So you can square a binomial, a polynomial that has two terms is called a binomial, by squaring the first term, adding to 2 times the first times the last, and adding the last squared. So if we applied this rule, we could have gotten this quickly. We would have had the first one squared, which is 8 squared, plus 2 times the first one, which is 8, times the second one, which is 9i, plus the second one squared, so quantity 9i squared. So we end up with 64 plus 16 times 9, which is 144i. Let's make sure. Okay, and plus 9 squared is 81, and I squared is just I squared, which we know is -1. So we end up with 64 minus 81, which I believe we did earlier, right? -17. Plus 144i. So that's one way. Another way is just to directly use the table method on that expression itself. So we would just put 8 plus 9i, 8 plus 9i, and we would just go ahead and multiply it like a times table. So we get 64 plus 72i plus 72i, and then plus 81i squared, which we know is 81 times -1, so -81. So now we can see we can combine these two, and we can also combine those two, right? So once again, we end up, of course, with -17 plus 144i. So just a couple of alternative methods of handling that in case you were interested. Okay, let's go back. All right, so this last one is a very popular form. These two kinds of expressions where the only difference between them is the sign between the two terms, they're called conjugates. Because we're dealing with complex numbers, they're called complex conjugates. So we can go ahead and just distribute, and then we'll get back and show you something else as well. So we get distribute the 4, we get 16 minus 32i, and then we distribute the 8i, so we get plus 32i, and then minus 64i squared. I squared being -1, so we get 16 minus, these two cancel out, right? So plus 64, which is 80. Now, this we're going to look at in a minute, in a different way in a minute, can be done very quickly if we remember something together. So let's move on. All right, as I was saying, the complex numbers a plus bi and a minus bi, they're called complex conjugates. of one another. So it's a mutual relationship. A plus bi is a conjugate of a minus bi, and a minus bi is the conjugate of a plus bi. When you multiply these conjugates, what happened in the previous problem happens every time. So you end up with a squared minus bi plus bi minus b squared I squared. That's of course -1, so you get a squared minus b squared times -1. So you end up with a squared plus b squared. So whenever you multiply two conjugates, you're just going to get the sum of the squares of the real part and the imaginary part, which is very handy. So we can do this very quickly now. 2 plus 3i times 2 minus 3i, we know that's just going to be 2 squared plus 3 squared, which is 4 plus 9, which is 13. So this is a way that we're going to use to rationalize the denominators when they contain complex numbers as well. So here we have 7 minus 5i times 7 plus 5i, so of course we get 7 squared plus 5 squared. So 49 plus 25, which is not 13, hold on. I don't know what I was thinking there. It's 74, okay? And same here, 11 squared plus 2 squared, so 121 plus 4 or 125. This is a very handy trick to have in your bag of tricks because we'll use this often, okay? Now, dividing complex numbers is an interesting venture because remember, whenever you have a complex number in a denominator, you basically have a radical expressions. Remember how we used to simplify radical expressions? We did precisely what's called rationalizing of the denominator by multiplying by the conjugate of the denominator. Now, that's when you have two terms. If you have one term, it's easier. If I have an I there and I want to get rid of the radical in the denominator, all I need to do is multiply it by an I. So here I'm just going to multiply this. I'm going to say that's equal to -8 over I times I over I. Of course I can do that because that's just 1, and you can always multiply by 1, right? So on the top, we end up with -8i. On the bottom, we end up with I squared. That, of course, is -1. So we get -8i over -1, which is just 8i, positive 8i, because negative divided by negative is, of course, positive. So to get this one, we're going to have to multiply by the conjugate. So dividing complex numbers is more like just rationalizing the denominator. So we're going to multiply by the conjugate, which is 1 plus 6i. And on the top, we have 1 plus 6i. So we get 2 times 1 plus 6i on the top. Down below, remember, a minus bi times a plus bi is just a squared plus b squared, right? From the last screen, right? So that's just going to be 1 squared plus 6 squared, so we get 2 times 1 plus 6i over 1 plus 36, which is 37. Now, I noticed there is no cross-canceling possible. I left the 2 out in case I was able to, I became able to cancel it. I would have done that, but we didn't end up doing so. So we're going to go ahead and just distribute it. So it's 2 plus 12i over 37, which we can break up and write as 2 over 37 plus 12 over 37 and put the I on the side so that we're in standard complex form, okay? Same here, you should be able to do this now. Go ahead and try it. Multiply by the top and bottom by the conjugate of the denominator. So in this case, 4 minus 2i, and see what you get. All right, so 4 plus 10i over 4 plus 2i times 4 minus 2i on the bottom and 4 minus 2i on the top. Of course, we're just multiplying by 1. Anything over itself is 1, so we can do this. So the top, we go ahead and multiply it out. Let me do it using the table here. So I have 4 plus 10i and I have 4 minus 2i. So I can multiply it quickly. I get 16 minus 8i plus 40i, and then negative 20i squared. I squared is negative 1, so this becomes negative 20 times negative 1, or positive 20. So now I can combine the 16 and the 20. I can also combine these two, right? So we end up with 32i, well, 36 plus 32i, right? So on the top I have 36 plus 32i. Down below, of course, I have a plus bi times a minus bi, so it's just going to be a squared plus b squared, right? So 4 squared plus 2 squared. So we get 36 plus 32i. That's 16 plus 4, which is 20. Now, I look for a common factor with all three of these, and I notice that that would be a 4, right? So let me go ahead and erase this down here now that we're done with it. So I'm going to go ahead, because the common factor between 36 and 32 is 4. I can't go for 8, that's too much, it won't go into 20. So I'll just factor out a 4 on the top. That leaves me 9 plus 8i over 20. Now I can cross cancel the 4 and the 20. That leaves me a 5 down below. So now I'll write the answer in standard complex form as 9/5 plus 8/5 I. And that's it. That's all you have to do. So there we just divided those two complex numbers by rationalizing the denominator. Now how about this one, I to the negative 13? Well, remember we have a rule that says x to the negative n is 1 over x to the n, right? So I'll go ahead and write that as 1 over I to the 13. Now if I just multiply by I on top and bottom like this, I end up with what? With I over I to the 14. From early in the video, you should remember how to deal with that, right? That's I over, I can write I to the 14 as I squared to the power of 7, right? So that's I over negative 1 to the power of 7. Now negative 1 to an odd power is just negative 1. So that's I over negative 1. And it'll be nicer if we just write it as negative I, like so. All right, so that's how you divide complex numbers, or simplify a complex number looking like that, okay? All right, here's one last bonus problem. I just wanted to make sure you can handle something like this and write it in standard form. So the square root of negative 128 we'll deal with by taking the prime factorization of 128. Now we can start with 2. That leaves us 64. 2 again gives us 32. 2 again 16. 2 gives 8. 2 gives 4. 2 gives 2. And 2 gives 1. So I have 2 to the power of 1, 2, 3, 4, 5, 6, 7. So if I lump 6 of them together, that'll be a perfect square, right? So we'll go ahead and write this as negative 8 plus, we're going to go ahead and break up the square root of negative 128 into 3 radicals. Remember, we put the negative in the last one. We put the 2 to the 6 into the perfect square one, and we put whatever is left, which is just 1, 2, into the non-perfect square radical, meaning the radical where the radicand is not a perfect square. So now we get over 4. Now that's going to be negative 8 plus, now the square root of 2 to the 6. What do you square to get 2 to the 6? It'll be 2 to the what? 2 to the 3, right, by the power rule. So that's just 2 cubed, radical 2, and square root of negative 1, we just write it as I, right, over 4. So we end up with negative 8 plus 8 radical 2I over 4. I noticed that these three factors have a common factor of 4, so that'll be the good thing to factor from the top. So that leaves me negative 2 plus 2 radical 2I over 4. Now I can safely cancel the 4's, and we finally end up with negative 2 plus 2 radical 2I, just like that. Okay, so if they ask you to simplify and express the answer in standard form, that's what you would need to do. All right, so that should do it for this video. You take care, and we'll see you for the next lesson.